I want to introduce Dr. Rafi Nazikian. He is the Senior Director for Data Science at General Atomics. Quite a few people at GA are at SDSC now and vice versa. So we have a good relationship with that company. Before coming to GA, Rafi worked at Princeton Plasma Physics Laboratory, and he completed his doctoral studies at the Australian National University. You might hear the accent. At GA, Rafi leads several R&D efforts, including today's topic, operationalizing AI and digital twins to accelerate discovery and de-risk the path to commercial fusion. You'll learn today about fusion and find it to be quite interesting and exciting. Rafi is also a fellow and twice distinguished lecturer of the American Physical Society, twice recipient of the Cowell Award for Excellence in Plasma Physics, author of over 260 research papers, a senior research manager and part of the GA Mentor program. Mentoring at a lot of national laboratories is a very important concept, as it is here at SDSC, which is why we have these webinars and these events like this. So without further ado, I'll turn the control. You're welcome. I'm so glad you're here today, Rafi. I'll turn control over to you to start screen sharing and begin talking when you're ready.
Thanks so much, and thanks everyone for being here. I hope that this is both informative and entertaining. It certainly was a pleasure for me to put this material together, and I look forward to sharing it with you.
Rafi, sorry, I forgot to mention that we'll hold questions till the end of the talk, but there is a chat. You can type any question you want to ask at the moment. Then at the end, we'll go through them one by one and have plenty of time to answer all of your questions. So feel free to put them in the chat. Okay, Rafi, now you do have controls.
Thank you very much, everyone. Let me go into full screen here. So let me just say that this is a very exciting time for fusion and for science in general. We know that fusion in the last several years has attracted enormous attention through private industry investments, but also through the government engagement and the Department of Energy. And most recently, we now have the announcement of the Genesis program, and the Genesis program holds out the promise of dramatically accelerating scientific discovery, time to insight, and ultimately the delivery of fusion energy to the grid. So with all of this excitement and the work that we've been doing internally with our collaborators, including UCSD and SDSC, the American Science Cloud, and of course with the Department of Energy, we've got some very interesting developments and perspectives, and also I think extremely important opportunities for all of us when we look forward to what can be done in this space of AI and so-called digital twins. So the obvious goal for fusion is limitless carbon-free energy at commercial scale. One of the key bottlenecks, and we know that there are bottlenecks, it's a major constraint actually, is the reactor scale trial and error is too slow and costly. Furthermore, traditional simulations tend to be siloed from engineering and design. So if you think about the AI opportunity, it is how can we de-risk the path to commercial fusion by moving risk from costly physical trial and error, particularly at reactor scale, to in silico optimization. And the ultimate promise of AI and digital twins is that we can accelerate the deployment of fusion energy and other technologies through the power of, again, AI. And this is really the promise, but it's also the opportunity that's presenting to us through new programs like Genesis, for instance. The important opportunity that we have right here is the DIII-D National Fusion Facility. the D3D National Fusion Facility is a mature, extremely well-diagnosed, highly flexible facility for performing cutting-edge fusion research and development. And by using this facility, we can, in fact, operationalize AI and digital twins to de-risk the path to fusion energy development. It's an incredibly valuable resource that we all share that belongs to the nation. This is just on the right-hand side. I wanted to share some beautiful imagery, perhaps the most beautiful imagery I've seen actually, of fusion plasmas. Of course, the image on the top is the beauty of solar flares, where highly ionized gases called plasma are bound to magnetic field lines and they reveal magnetic field lines. At the bottom, you see something quite analogous, which is when material is injected into the jet tokamak, which is the massive fusion experiment that has recently been decommissioned in the UK. You can see these, what I would call fires of plasma. It's both beautiful and it's awesome in terms of the power that plasma stores and can bring to humanity when tamed appropriately. So here is the scaling barrier that I was referring to. And ultimately, it's what I refer to as the unacceptable cost of physical iteration at reactor scale. This is a beautiful demonstration of the risks that we face, particularly with larger fusion devices that are prone to what we would call knife edge instabilities. This is actually a movie, an infrared movie taken in the TFTR device back in the 1990s, showing what would happen what actually happens if you hit one of these knife edge instabilities and trigger the very rapid loss of plasma stored energy to the wall. And you can see at the very end of this process that there is, in fact, a very strong interaction with the wall that requires what we would call unscheduled maintenance, right? That brings down operations. You have to go in there, you have to repair it, and you have to come back up. Now, here is an example in another device in Europe called ASDEX upgrade, where the result of these knife edge instabilities that can release large amounts of energy to the walls, that can lead to surface damage, that can bring down operations and require unscheduled maintenance. Now, these kinds of events still occur, and it's important to understand that while these events are manageable in present-day experiments, they become relatively unmanageable at reactor scale. So this TFTR experiment on the left, there's roughly 2 to 3 megajoules of stored energy in the plasma. A reactor will typically have 100 to 300 times this level of stored energy. And so you can see just from the observation of this scaling, how stored energy scales as we move to the reactor regime, the challenge, essentially the unacceptable cost of physical iteration. So I think this really brings home the essential challenge, but it also raises the opportunity, because right now in devices like D3D, where we have roughly a megajoule or so of stored energy, we can use these facilities that are relatively robust to these phenomena and that are extremely well diagnosed and highly flexible. We can use these facilities like D3D as a test bed for the development of AI and digital twins. So we proposed D3D as the initial proving ground, and this is in fact what we've been developing, and that will show you the progress that we've made. The other aspect of these again, facilities like D3D, is, again, they're an ideal testbed for agile AI technology development to de-risk and validate AI models for fusion. And I'll discuss a little bit more of this. Now, the D3D, you guys are all very familiar with it. We've got tremendous collaborations across the world, unmatched control and diagnostic capability, high operational cadence, which means you get a lot of data. You can generate a lot of data. You can develop a scientific proposal, go into the control room and get the data that you need relatively quickly. And again, because of the amount of stored energy, roughly a megajoule versus hundreds of megajoules in a reactor, you've got this resiliency. So you can actually do your trial and error in the physical world and develop your AI models and validate your AI models for extrapolation. So what do we want to actually demonstrate on a platform like D3D? First, what I'm showing you on the right is an amalgam, if you will, of the physical facility with plasma models and the CAD of the actual facility. So we've got here, this white is essentially a point cloud of laser metrology that shows the as-built geometry of the 3D inside of the D3D vessel. We've also got surrogate models of the plasma state. And we also have ultimately the CAD of the facility, which is the design. And so we can bring the as designed together with the as built, together with the surrogates of physics models, together with the experimental data to create a kind of a single ground truth of the facility, which is extremely powerful. But what do we want to demonstrate with this? First, we want to demonstrate that we can accelerate time to insight. We want to demonstrate that we can maximize scientific availability of the facility. We want to be able to minimize costly redesign. And we want to be able to combine all of these factors to validate the tools that can be used to de-risk commercial fusion. So what does the digital twin on D3D actually look like in terms of its blueprint? So this is basically the architecture of the digital twin. The digital twin it's not just a representation of the physical asset. This is a very important distinction that we need to make. If you really want to twin the facility, you need both a representation of the physical asset, but you also must have a virtual representation of the entire control system, because ultimately fusion plasmas need to be controlled. So here we've got a representation of the physical D3D system, which involves both the physical asset, but also the control system actuators, plasma, and sensors. And of course, we have the control room, and the control room interacts with the physical facility. On the other side, therefore, we must have a virtual representation of that physical asset, the control system, virtual representations of that, the actuators, the plasma, and sensor models. All of these are models. The virtual control system, we just succeeded in containerizing that. So what we've basically done is take the physical control system, virtualize it, in other words, represent it in code as a high-fidelity representation of the actual physical control system, and then containerize it so it can actually be run in the cloud. This is, I think, a very important capability that we will plan to exploit in the future to, in effect, democratize access to these tools and have community-driven development of models and their integration into a twin as we build out this twin capability. But beyond that, we also need an interactive visualization layer, and this cannot be understated. The importance of bringing the facility data to bear on the modeling data in real time or near real time is extremely important element of driving scientific insight, and I would call multi-domain collaboration. Then as an example for the plasma models, we would have shaping models, that is how the magnets of the facility interact to shape the plasma. Then we have transport models. These are models that represent the fundamental internal transport processes so that when you apply auxiliary heating or actuators, it can figure out iteratively what the plasma state should be, including stability models, exhaust models, and of course, material interaction models and their integration. And this is something I will come back to a little bit later. Finally, there's a cognitive layer. Let's call it a deep agent. I used to call it a co-pilot, but that indicates something commercial, right? So the cognitive layer is a very important layer, because what we have here on the left-hand side are basically very simple reflexive models that execute, that are essentially surrogates of sophisticated simulations, but they're not generative models. So they faithfully execute, essentially provide representations of the underlying simulation. The only generative model in this loop, because generative models, clearly there's issues with them. We don't want them to hallucinate across the board. So the cognitive layer here is how the control room experts or machine operators interact with all of these models, where this cognitive layer understands LLM-driven instructions, and it can execute these, in a sense, deterministic models to provide a synopsis or guidance to the control room or to the planning process even before the experiment. So this system is actually coming together quite nicely as well. And ultimately, where do these models come from? They come from us. They come from you. They come from everybody. These models that we are integrating into the twin is the treasure house of decades of fusion energy research funded by the Department of Energy. And so ultimately, the success and the value of this enterprise depends on the entire community being able to participate, contribute, and benefit from the work of others. And it ultimately also depends on being able to provide these tools and services and modeling capabilities that industry can use, that they can import into their protected IP spaces and generate their own IP from the publicly available research that is made available, again, through these surrogate models and through this infrastructure and its validation. And that really comes through the American Science Cloud. And so much of what we've done is also work with the American Science Cloud, now called American Science Cloud Pride. It's basically working with the major OSCAR laboratories and centers to integrate workflows such that we can automate and operationalize models and data analysis into this twin infrastructure. So accelerating time to insight. What is the leading indicator of accelerating time to insight? Here is an example where we've started this process, maybe also now almost starting this almost 3.5 years ago now, where we discussed with the DOE and with OSCAR Labs how we can automate data-intensive analysis such that we can, in a sense, open the floodgates, if you will, to rapid, high-fidelity modeling and simulation analysis that can feed into AI models. So here is an example of work that we did with Princeton University and Argonne, NERSC, involves ESNet, Oak Ridge, where we took the very labor-intensive workflows to develop plasma state inferences. And we were able to automate it such that we've just orders of magnitude more, again, high fidelity data became available that can then feed into these downstream simulation studies and to build surrogate models. Just to give you an idea, we, as a program, with all of the collaborators working together, we developed about 4,000 plasma state reconstructions in a 12-year period. It's very labor intensive, but with only 4,000, that creates an incredible bottleneck to the kind of simulation and validation you want to perform at scale for AI and digital twins. So in this intervening period of a couple of years, we now have operationalized an automated high fidelity reconstruction capability. And we've generated now in excess, I believe, of 1.6 million high fidelity reconstructions. And this fundamentally changes the game. And so part of AI is take labor intensive processes, use AI to automate them, and then have in particular, the physicists and the engineers operate at a more integrative level of strategic thinking and decision making, but try to automate all of these processes so you open up the pipeline, if you will, to detailed analysis. This was a really very successful development, and it was highlighted on a number of occasions by the DIII. Step two is then to create this interactive visualization. And here I want to thank NVIDIA folks in particular. They've done a tremendous job. And I have to say it was not easy for anyone to put this together. What this is an assembly of design CAD drawings, if you will, of various aspects of the facility that had to come together in order to provide a single representation that we can use going forward to overlay simulation results and experimental measurements. One thing that we learned here is that bringing all of this data together is not straightforward, and it was not straightforward, particularly when you bring data in from diagnostics. It's a very interesting situation where even different diagnostic systems use different coordinates. It's not a common coordinate system, so you have to map all of these things together in order to build this, if you will, common ground truth. But once you have it, it's extremely powerful because it allows, again, interactive visualization, which is very valuable for multidisciplinary collaboration and problem solving. This is an extremely powerful tool. So it's visualization, and it's more than visualization. And I'll show you an example of how that goes in the future. Let's go to the next one. So now that you have the facility itself, you want to be able to go from fragmented data to unified intelligence. So here is a glimpse of the complexity of diagnostic measurements in a fusion device here, the DIII-D facility. We've got on the left-hand side, you can see really the complexity of these different diagnostic sensor packages. There's over 50 sensor packages on DIII-D. Only 6 are shown here. Each sensor package has its own team of people that work to extract high fidelity information on the plasma state represented by that information. But bringing all of this together is something that up until now has really been a very bespoke, labor-intensive solution. We can have different groups working on different diagnostic packages, extracting different perspectives on the underlying plasma state. But putting these together has so far been a very bespoke, labor-intensive, usually binary process. So here is an example of one thing that we've done with our friends at Livermore. Particularly, I want to recognize Charlie Lanier, where we've got this beautiful infrared camera data, and we want to be able to map that into the physical geometry of the physical asset, the virtual representation of the physical asset. And we want to be able to combine that with other diagnostic data to provide a coherent, integrated representation of the facility. And this kind of thing then will allow us in the control room to be able to see the physical truth in almost real time that can be extracted from different systems, juxtapose them, and understand what each other group is seeing and form in a much shorter time frame, a more integrated view of what's happening in the physical asset. So it's both an interactive, I would say, a visual tool, but it's also interactive across expertise and domains of knowledge. And that interactivity across groups is as important as the interactivity of the individual with the virtual asset. So what's the proof point here? So here are some examples of the past where we can then integrate the simulation capability that is afforded with the digital twin infrastructure with the examples of events in the vessel that had not prior to been fully visualized. And here is an example of two events, one where a weld was broken because of excessive heating due to ion bombardment. And on the left-hand side is excessive heating due to neutral beam shine through. Now, the usual engineering approach is that you identify a couple of plasma states, if you will, to validate a design. But with the digital twin, you can actually run thousands of plasma states because it's now fully automated with surrogate models. And by doing this, you can obtain analyses that looks very compelling, which is the predicted power loads on plasma-facing materials, as an example, can be predicted with very high fidelity if you can then run thousands of simulations or thousands of discharge conditions instead of one or two test points to identify these things. And this kind of development is extremely important to validate the underlying models and to show how these models can contribute both to the design of experiments and towards the de-risking of fusion development in general. So then improved system monitoring. One of the most important applications of AI is to try to move from a reactive maintenance footing to a predictive maintenance footing. And here is an example of that. I don't have much time to dwell on this, but I just want to show you that very nice work done by Kishan Rajput at Jefferson Lab, showing that he can actually, with his model using continuous learning, he can show sensor drifts in this case, on a magnet on DIII-D that shows deviation from normal operation before an event occurred, such as the loss of pre-stress of a magnet. So by using AI models to develop sophisticated threshold monitors and alarms in a multi-dimensional sense, you minimize your false alerts. You maximize your true positives so that you have a reliable monitoring system based on the ability of AI models to produce complex multidimensional monitoring systems that go well beyond the reliability, well above the reliability of traditional threshold detectors. And this is something that's actually extremely important and that we're developing as well through DOE funding. Enhanced control. Now, I want to highlight here some wonderful work that's been done on D3D. Actually, this is from K-STAR, but in fact, this week or last week, Egerman's group also performed this experiment now on D3D, where what you do is you say, if there is a measurement that's critical to plasma control, and in this case, it's radiation measurement that's critical to the control of detachment, in this case, in the K-STAR experiment. What they've done is they've looked at the correlations between different sensor signals to reconstruct an original sensor that's critical for control, such that when that sensor signal fails or stops operating, the control system can take over with a synthetic sensor signal and still maintain control. And this is a wonderful demonstration by Egerman and his group here of how they can use correlations across different diagnostic packages to reconstruct a sensor signal so that you achieve robustness to what is called off-normal events. And so this is really fascinating. And again, as time marches on, when the box says diagnostic failed, it actually means that the diagnostic that measures that radiation front failed, and yet the control is still maintained. And that's extremely important capability. But what this also does is it demonstrates that there are very powerful hidden correlations in data. And you can use those hidden correlations to develop very powerful tools for maintaining robust control. And ultimately, you can use that information for designing robust diagnostic capabilities in future reactors that are also resilient to off-normal events, which is very important for maintaining operational reliability. Now, very quickly, what this work essentially shows is that there's some hidden low-dimensional representation of the entire diagnostic set that you can make use of. So by this process, we believe, and Egerman's group believes, that we can in fact build massive multi-layered transformer models to take all the sensor data and to here, when you go from left to right, all the sensor data comes in here. You should be able to reduce the dimensionality of the space, create some low dimensional latent space that reproduces the signals. And then you can lock that down to produce all kinds of models that you want in a self-consistent way. And this fundamentally makes use of hitherto hidden correlations between different diagnostic systems because there is some low dimensional latent space in the system that can be exploited. I would also say that this highlights a challenge as well. And it's something that I will pivot to soon, because the challenge here is you're making use of correlations where the data is substantial. So you're really looking at in-distribution correlations. But much of what we do in scientific research and in fusion is looking at regions where data is sparse and where you may not necessarily be able to rely on correlated behavior in distribution. And this is an extremely important point I want to come to towards the end here. So the next step is optimizing scenarios. So if we look at this, we've got these physics models. So how do we want to use these physics models? We want to be able to have these physics models to represent the plasma state, its stability, its transport, exhaust, material interactions. Why? Because we want to be able to develop in a principled way, open loop and closed loop control capabilities. And that is this box up here. It's the control system. What's the control system? It's the open loop actuated trajectories, and it's the closed loop control. So what we want to be able to do is to optimize this in silico and then do it once and do it right in the control room. So as an example of the first thing here, which is shaping, so on D3D and on a model that's been actually exploited across the fusion community is called GSevolve, and it does the basic predictive plasma shape control modeling that goes into nearly every experiment that is executed on D3D or almost any other device in the US and also internationally. And this enormously de-risks planning for experiments, but it's quite slow. So the first step here is to develop a surrogate of this control model that can execute very rapidly to be able to inform control room decisions. Then the next step on top of that is to build these models, stability models, transport models, exhaust models. And here is an example. We've got Sol PS Ida at Oak Ridge. We've got U-Edge being developed at Livermore. We've got C-Gyro being developed here at GA and at UCSD as well. That's a terrific partnership. We've got M3DC1, stability calculations, modeling capability. That's also being developed at UCSD, PPPL, elsewhere. These are all national collaborations. So these are sophisticated, validated models that we want to distill into surrogate models and integrate into this digital twin workflow. Here is an example of what enables this kind of sophisticated model integration. Here's the example of C-Gyro. C-Gyro has been optimized over the years to be very finely tuned to execute efficiently on the latest GPUs. And what this has enabled over the last decade is at least an order of magnitude increase in the kind of spatial and instability fidelity that this simulation capability can resolve. It's really quite remarkable. And the model is also feeding into both EDA design and also into the, as an example, the Spark physics basis. And it's primarily because of the enormous investment that has been made over the last decade or so in transitioning from CPU to GPU and optimizing models like C-Gyro so that now we can actually have simulation farms, if you will, and we can generate many of these simulations to integrate into surrogate models that can be pushed to the edge and run more or less real time on the facility looking at actual data. And here is an example of a surrogate that was recently developed, and I want to call out Professor Rose Yu. She's led wonderful work with our Tom Neiser over here, developing a surrogate model for C-Gyro that integrates thousands of various runs to produce, in effect, a profile predictor that can run nearly real time. So why is this important? It's important because, you know, it can take hours to run a single C-Gyro simulation that can give you the turbulent transport properties at a given location. But by building this surrogate, then we can almost instantaneously, within a millisecond, predict an entire profile and how it responds to actuators. So this is a very important development, and we're thrilled to collaborate with Rose and her team. The other thing that I want to point out, though, is in order to develop this closed loop predictive optimization, we must extend these models to the walls. Everything that you see here on the right-hand side is the result of material interactions. You can see the infrared imaging from the inside of the D3D vessel, where the plasma interacts with the material walls, heats the material walls. These heating regions then expel material from the surface that can also interact with the plasma core. Here on the left-hand side, there's some beautiful imagery of lithium powder being dropped into the plasma that affects the stability and performance of the plasma discharge. It also makes for excellent Christmas cards, by the way. But everything that you see here is the result of material interactions. And here I want to highlight some of the terrific work that's being done by Smirnov and Krishnikov on this face code, first of all, simulation code. These are the kinds of things that we have to integrate with scrape-off layer models, that we then have to integrate with core transport models, with stability models, so that the wall and the core plasma speak to each other. And so this kind of work really requires a much deeper collaboration across domains, which is required to bridge materials with core plasma to develop truly performant simulation capability that can be validated and extrapolated. So this is just a brief view of how the current digital twin runs. So I showed you the loop here. We've got Mark Kostuk, the GA fellow that's very much involved in the development of this system. We've got this digital twin running now in the control room. We've got the plasma control module, actuator modules, plasma modules, and then synthetic sensors. This then goes into a closed loop, and then we can visualize the predictions in the interactive visualization layer. And this is actually a screen grab. It shows how fast the actual model sequence of models executes in the control room. It's just a straight screen video grab. So it's basically going at real time. So we're taking models that take a very long time, not geological, but probably on the time scale that we need to develop fusion, you could call it geological. And we can push it to the edge and bring it into contact with experiment and execute them in a sense that it's almost real-time capable. But it doesn't stop there. So one of the most important things that we have to develop, and we're developing now in collaboration with Ryan Coffey at Slack, who's got this wonderful collaboration with NVIDIA, right? So I gave this talk at GTC, so I had to cross that there. So the real goal here is massively parallel inference for faster than real-time forecasting, both for planning and for real-time control. Just think about this. What you have a very complex dynamical system. You have to optimize your feed-forward open-loop actuated trajectories and minimize the work that your feedback loop has to do, right? The harder your feedback loop has to work, the more oscillations and the more unusual and uncontrollable behavior you're going to end up having. And so what you really need to do is optimize every time point. You want to be able to launch, in effect, thousands of forecasts and then invert that to determine, again, at every time point that matters for the control system, what the open loop and closed loop trajectories need to be. And this is where we're going, and it will be an extremely valuable capability, both for the digital twin, but also for the real-time control system, because then when you optimize the pulse planning in the twin, you should be able to flip a switch and have it execute in the in the real plant. And here I want to call out both SLAC here, but also Oak Ridge. So Ryan works very closely with Oak Ridge, and we are very thrilled to be working with Oak Ridge actually on multiple levels. The other is where this goes. It's once you validate all of these capabilities, you then want to demonstrate how it de-risks design. Now, so far, we've been dealing with operating facility. It's not a design challenge, except when it is. And this is an example of what design activities currently look like for various upgrades planned or for the near future and for longer term upgrades on D3D. This is modeling that's done using SolPS. Bob Wilcox and others at Oak Ridge are involved in this sort of upgrade planning, particularly for diverter upgrades, in particular, one for what's called negative triangularity diverter, and the other, which is the, I think it's the chimney diverter. So all of these need modeling. The goal here, what we want to be able to do is integrate the digital twin capability of running, in effect, thousands of discharge conditions to fully explore the operational space of the device with these upgrade models to then feed back into the design process. And this is ultimately what the value proposition is for digital twins in a fusion reactor, for validated digital twins in a fusion reactor environment. What we want to be able to do by validating upgrades, not only operations, but also upgrade plans, is that the ultimate vision is that you will in fact be able to operate a future fusion facility in silico and in fact train your operations team, train your maintenance team to operate the facility before you cut metal. The time it takes to bring a new facility up, I remember talking to my colleagues, it's almost universal. The comment is that it typically takes 10 years to figure out how to operate optimally or reliably operate a new fusion facility. We don't have 10 years of learning on the job. We don't have the luxury of building a fusion facility and then figuring out how to run it. We have to move in parallel. And what the digital twin does, assuming that the underlying models have been validated at the appropriate scale, is it allows you to actually both de-risk the design, but also get a leg up in operations by operating this thing in silico while you're in fact constructing it and using that operation to de-risk construction. And you do this through integrating digital twins into what's called digital threads, which is really engineering design for product lifecycle management. And then you've got a very powerful infrastructure that you can leverage to de-risk fusion. So some final thoughts, and thank you very much for your time. The AI is almost magical, right? And the example that I showed you earlier of hidden, if you like, some hidden low-dimensional representation of the system that could be used to reproduce multiple sensor, to develop sensor models that can demonstrate resiliency. This sort of thing, it's almost magical, but it arises out of deep correlations from data in distribution. And this is an ultimate challenge because scientific breakthroughs, the way we operate these facilities, we don't operate these facilities in distribution. Yes, there is a distribution of data, But to say that the data is complete, and therefore all you need to do is hand over the data and we can build these massive models that can give us all the answers, is in fact incorrect. We operate these facilities to push the boundaries of understanding, to push the facility to where data is sparse, to extract insights in regimes that have either sparse data or no data. That is, in fact, the scientific method, right? So the ultimate challenge for physical AI, and everything that I've spoken to today is really physical AI, is principled out of distribution extrapolation. And this is precisely the area that is most challenging for physical AI. Now, there's enormous amount of work being made in developing physics-informed AI models, right? But it's a very rapidly evolving field. And it's a fundamental challenge, how to develop AI models that make principled out of distribution extrapolations. Fusion data is abundant. So, in the Genesis context, you will read that there's enormous amounts of fusion data, or there's enormous amounts of data across the DOE complex, and it's true. But relative to the data that goes into LLMs, it's relatively sparse. It's relatively sparse. And in the edge cases where we do science, it's even more sparse. So fundamentally, when we talk about validating AI models and digital twins, we're really talking about the primacy of the experimental facility and the primacy of the scientific method. That you have facilities like D3D, like other experimental facilities, that are designed to probe the outer boundaries of what we know. And these facilities are critical to validate the predictive power, the principled extrapolation power of these models in order to de-risk their application at fusion scale. It gets, again, it all comes back to the scientific method, and I want to emphasize that. So again, I think from the strategic horizon point of view, the convergence of digital twins with physics-informed AI, I think will really revolutionize every aspect of fusion R&D, as it will every aspect of science and engineering. I will also emphasize that fusion facilities, experimental facilities are absolutely critical, because the scientific method holds primacy over everything else. If you develop an AI model, you want to be able to validate it by making out of distribution predictions, going to a facility and testing it. The scientific method rules above all. And that's the way we're approaching this, to deploy rapidly, to learn fast, to iterate quickly, and to transfer that knowledge to the broader community and to industry. Thank you.